My name is Feng Kang from Johns Hopkins University. Today, I'm happy to talk about our work here called Probe the Proto, measuring client-side prototype pollution vulnerabilities of 1 million real-world websites. So first of all, I would like to tell a story. So suppose you are a boat lover and you really love sailing on a boat. It could be sailing on the sea in San Diego under the sunlight out there. Then one day you receive an email, and it is encouraging you to click on this provided link for a boat purchase. Then you think, oh, this should be cool, and click on the link without hesitation. Then all you see is just a normal boat sailing page. However, in the meantime, you are not aware that by the time you click on that link, you are automatically sending your credentials to a hacker somewhere in the world. And the hacker could say, haha, it's super easy to get the credentials. All I need is just prototype pollution vulnerability and cross-site scripting. Oops, this is not good news for you. So what's happening over there? This story involves a zero-day vulnerability found by us and has not been fixed yet. This zero-day vulnerability involves a website called borderboats.com, which is an authorized dealer of malleable boats. After we responsibly disclosed this vulnerability to them for multiple times, they haven't replied to us yet. The exploit is as follows. So it contains mainly two parts. First part, the __ proto _ bracket k part, which is responsible for prototype pollution. The second part is the malicious script part. Here we use the alert function to replace the real malicious script part to avoid any real damage to this website. Let's see how this exploit works in the real world. This short video will show after I click on that URL, an alert pop-up window will pop up on this web page, so that this is clearly a sign of cross-site scripting. So why does the exploit even trigger the prototype pollution and then the cross-site scripting consequences? Let's take a closer look. So first, let us look in reverse from where the code is injected, which is where the cross-site scripting happens. So first of all, we have an object called data, and it contains some benign properties. Then inside this for loop, it will extract all of the properties defined in that object data to store in the variables field. Then a cross-site scripting sync function, which is called element.append, will be called. Then it will append all of the data bracket field code into the dorm. So say that we can control this field, then cross-site scripting happens, because the malicious code can be appended to the dorm. However, the object data here is either constant or defined via AJAX from borderboats. So the question is how do we really exploit this cross-site scripting? The answer is through prototype pollution. So let us switch to the code snippet vulnerable to prototype pollution to see how it really happens. Inside this for loop, there are mainly two iterations. In the first iteration, the variable p will be set as the value here called _ proto _, which is injected by the adversary. Then O equals to O bracket p will be executed. Here, the variable O is initially an object, and then O bracket _ proto _ will point directly to the object of prototype, which is a built-in base object in JavaScript. Then in the second iteration, P will be set as an arbitrary key k, which is also injected by the adversary. Then the statement O equals to O bracket P equals to J will be further executed. Then the O bracket K equals to this malicious script will be executed. So what does it mean in the end? We successfully pollute the object.prototype.k equals to this malicious script. So this is how prototype pollution happens. Basically, it involves polluting the base object property in JavaScript. And such property further opens up a backdoor for the adversaries to actually inject some malicious script. Then we switch on to the code where cross-site scripting happens. So we already know that inside this for loop, all of the properties defined under the object data will be executed, including the object that the adversary has already injected. So here, data bracket field will equals to data bracket k, then equals to this malicious script. So that's how prototype pollution leads to cross-site scripting, because this malicious script will further be appended to the dorm. But here we have a question over there. So actually, data.k is not undefined. So actually, when data.k is not defined, how the data bracket k equals to this malicious script? The answer is through the prototype chain mechanism in JavaScript. So here, when data.k is not defined, JavaScript will further traverse the prototype chain and then find the data._answer portal__k, and then replace this value with the data.k. So that is why we see the data bracket k equals to this malicious script being successfully injected. Then besides cross-site scripting, what are the other consequences that prototype pollution could lead to? The first one is called cookie manipulation, which involves the document.cookie affected by a polluted property that is injected by the adversary. Then it could cause some impacts, such as session fixation attacks. Then the second one is called URL manipulation, which involves URL requests sent by the victim affected by a polluted property, such as URL requests sending from script.source and image.source. The impacts including parameter pollution, phishing, and etc. And there could be other more consequences that need to be discovered. Then we also talk about related works. So prior works also study about prototype pollution vulnerability and its detection. So it basically it's utilizing static analysis to detect prototype pollution in the server-side applications such as Node.js. However, there are three main issues. First is the consequences of prototype pollution is unclear. The consequences including the cross-site scripting, cookie manipulations, URL manipulations that we have described before. Then the second one is they study the server-side applications only, but they do not study the client-side prototype pollution. The last one is the static analysis mechanism is not scalable or accurate for the client-side detection. Then we talk about our design on detection of client-side prototype pollution and its further consequences. So the core idea is the joint taint flow analysis, which is also part of our novelty. Here we show the adversary-controlled inputs as well as the vulnerable code location over there. The inputs looks like question mark underscore portal underscore bracket k equals to this malicious script. And in the first iteration, O equals to O bracket P will be executed. We mark it as the first sync function for prototype pollution, namely the object lookup. Then the second one, O bracket P equals to J, will be executed during the second iteration. We mark it as the second sync function for prototype pollution, namely the value assignment. Finally, we also append the cross-site scripting sync, which is the append function to this slice. Then the first data flow is the underscore portal underscore flowing into the variable P in the first sync function of prototype pollution. After that, the object taint flow is the variable O flowing from sync function 1 to sync function 2. After the variable P is being set to the underscore portal underscore, then the variable O will point to the object.prototype in JavaScript. The second data flow is the variable, the string K flowing into the variable P in the second sync function. And the last one, the malicious script flowing into the variable J in the second sync function, and then to the cross-site scripting sync. So the term joint taint flow involves all of those three data flows as well as the object taint flow. And our analysis system is built on the top of joint taint flow analysis. It basically involves two main modules, the joint taint flow analysis as well as the result validation. So after our crawler iteratively crawls all of the seed websites, it will use joint taint-flow analysis to get both the taint flows as well as the exploits. Then after the result validation, it will automatically generate the technical reports to report to the corresponding website owners. In the first module, the input exploit generator is able to generate inputs for the dynamic taint engine to do the taint tracking. And then dynamic taint engine will provide sufficient information for the input exploit generator to generate next step input or the final step exploits for the result validation to validate. In the exploit validation module, the exploits for both multiplication and its further consequences will be further validated. Then we also provide defense analysis, which is responsible for studying how the real-world websites defend against the multiplication and its further consequences. So this is how our overall system architecture looks like. We also evaluate our tool under this 6 matrix. However, due to limited time, we only cover the measurement results in these slides. For other parts, please read our paper. For the measurement results, our system called PropTheProto has found nearly 3,000 zero-day exploitable vulnerabilities. After we responsibly disclosed all of those vulnerabilities to the website owners, 240 has already been fixed. Then we break down our found vulnerabilities by the consequences. So basically, there are 3 main types of consequences, namely cross-scripting, cookie manipulations, and URL manipulations, with the URL manipulations being the most prevalent one. We also provide some vulnerable domain examples here, namely the weebly.com, cnet.com, and mckinsey.com. The table also shows their rankings, status, and exploit codes. Note that cnet.com and mckinsey.com has already fixed their vulnerability after we disclosed those vulnerabilities to them. Then we also break down our vulnerabilities by the sources and sinks. For the joint taint flow sources, there could be multiple sources over there, such as URL search, URL hash, URL as well as the URL search, which is like document.location and location.search. And then there could also be cookies and the messages as the joint flow sources. Namely, the adversary injects the property by the document.cookie or by the post message function. Next one is breakdown by the sinks. So all of our 3 consequences have multiple sink types. For example, cross-scripting has 4 sink types, namely inner HTML, append, eval, and set attribute. So this is our measurement results, and we come to the conclusion. Our system, called PropTheProto, is the first large-scale measurement of client-side proliferation and its further consequences. PropTheProto discovers nearly 3,000 zero-day exploitable vulnerabilities, with 48 leading to cross-scripting, over 700 leading to cookie manipulations, and over 800 leading to URL manipulations. We responsibly reported all of the discovered zero-day vulnerabilities to their corresponding website owners. So far, 240 vulnerabilities have already been fixed. And we also open source our code under this PropTheProto repo. And we further provide a list of vulnerable websites that has discovered by us. Then we thanks to these medias for their media coverage of our paper. OK, thank you for your listening.